Hello, math humans. We're going to do 6.3a today. We're going to be talking about vectors. So our objectives are that we're going to look at the definition, the operations, and scalars of vectors. So a vector has an initial point, that's where it starts, and then a vector has a terminal point. So we typically represent vectors with the arrow or a ray, if you remember from geometry. So it doesn't necessarily mean that it continues, but that is going to be called our terminal point, but we draw it with the vector. Okay. So a vector has magnitude, lots of vocabulary words. Magnitude is the size of the vector, and so that could be maybe miles per hour, it could be distance. So magnitude is the size of the vector. Every vector can be broken down into x and y components, and then here's our theta. Okay, it's just right triangle trig. Notice that we're going to break our components, our vectors, down into components. They're always going to sit on the x-axis. Okay, alrighty. The terminal point on a vector is also called a head, and then the initial point is called the tail, and that will be relevant when we talk about putting vectors together. A vector is a directed, and that's why we have the arrow, so that's why we get our little arrow, line segment. So it has a specific beginning and an end. It has magnitude. I'm just going to go through these again because the definitions are important, which is size, and size could be distance, it could be speed, you could see the word velocity, all of those things. Okay, and then a vector also has direction, and if you'll notice, the direction is going to come from our x and y components. All right, the notation for vectors is we typically represent vectors with lowercase letters like U and then V and then W. They are typically bold, so you will see that in your textbook. Or you see that from, if I label this as A and this is B, you might see it labeled as A to B with an arrow over the top. And this shows the initial point, and this is the terminal point. Alrighty. Vectors are equal. Sorry. Vectors are equal if their magnitude and direction are the same. So two vectors are equal if their magnitude and direction are the same. All right, so if we take our little vector like this, okay, and we're going to say that this is 0, 0, and maybe the vector stops at 2, 3, we can take our vector and write it in component form. Okay, there's lots of different forms to write our vectors in, but for right now we're going to talk about component form. Component form is always going to be, I'm going to write it like this, x and y. Notice that the brackets are pointy. The brackets are specific. Remember that if I have curvy brackets, that means a point. If I have these little brackets, this means a set. And if I have pointy brackets, that means that it's going to be a vector. So the notation is very important. Okay? So my component form is always going to be terminal minus the initial. And we're always going to do like elements, okay? So the x's play together and the y's play together. So for the vector that I drew here, my component form of that vector is going to be 2 minus 0 and 3 minus 0, okay? This is the terminal, this is the initial, and so my vector would be 2, 3, okay? So that would be the component form of that vector. Other vocabulary words that you're going to see when we talk about vectors is magnitude. And remember that magnitude is equal to the size. And so magnitude is written with double absolute value bars, and that would be the size of your vector. So basically it's the distance formula, right? Because if the hypotenuse, it's a y, if the hypotenuse is going to be the magnitude of the vector, not the component form, then basically the magnitude is going to be the distance formula, sorry, brain fart. Or if we're doing it in component form, okay, so this would be the component form of the magnitude, meaning that I have no x1, it's just going to be x squared plus y squared. Okay, so if your vector is given to you in component form, then the magnitude of the vector is going to equal x squared plus y squared. Other words that you'll see when we talk about vectors are a unit vector, and unit means 1. So a unit vector has a magnitude of 1. All right, so we've gone through a ton of vocabulary. Let's start our first example. So example number 1 says find the component form and the magnitude of vector v that has an initial point of 4, 7 and a terminal point of a -1, 5. Alrighty, so I want me to find the component form of my vector. Remember, that's going to be my x and my y. My component form is always going to be terminal minus initial. Okay, that's important to remember. So it's terminal minus initial. So then my component form is going to equal, my terminal is a -1 minus 4 and 5 minus the 7. So it's going to be 5 plus 7. So my component form is going to be a -5, 12. Okay. So when we talk about the component form of a vector, as I'll just stop and take a little side note, I can draw that vector. This is a -5, and then this is 12. And then because we know lots of trig now, I can find the theta that's relevant to the vector. So I'll always draw my vectors. The magnitude is going to equal the square root of a -5 squared plus 12 squared. So it's going to be the square root of 169, which is going to be 13. I could also have just written that it was 13 because it's a Pythagorean triple, so it's a 5, 12, 13. All right, the next thing that we're going to talk about are vector operations. Sorry, you can hear the heater in the background. We tried to turn it off. There are two main operations. The first one that we're going to talk about, and it's the one that we're going to see a lot, are adding vectors. And I think it's really cool. I can do it mathematically, and I can also do it graphically. So another way to think about it is I'm going to be adding forces to determine what is the net effect. Okay. So let's say I'm driving my boat, and I'm trying to put my boat back on a trailer. So here's my trailer, my lovely artwork. So this is going to be my boat trailer. My boat is going to be out in the water. Okay, so this is my boat. And then not only do I have a boat and a trailer, I also, if we live in Flagstaff, we have wind, because wind is a persistent issue. And then maybe there's a current, and even though if you're driving a boat on a lake, there's always a current. So the boat has a force, the trailer is stagnant, but the wind has a force and the current has a force. And so my net effect, meaning that what's the force that it's going to take to get that boat back on the trailer, and if you've ever tried to do that, it can be entertaining. So it would be the component form of the boat added to the component form of the wind, added to the component form of the current, and the result is the boat on the trailer, which can be highly entertaining, and sometimes it's fun to watch. Okay, so these would be, we would add down. Okay, this is going to be something that we're going to talk about later, and then I would get my component form of my trailer. The other type of things, math operation that we're going to talk about for PreCalc is a scalar, and this is changing the size of a vector. And you can think geometry. If the number is, if the scalar is greater than 1, that means that the vector is going to increase in size. And if the scalar is less than 1, that means that our vector would decrease in size. All right, so now let's go back and talk about vector addition. Ooh, let me get a pen. So for vector addition, there are lots of different ways to think about adding vectors. And so let's go back and have maybe a couple of different vectors. So let's call this vector V, and maybe I'm going to call this vector U. Okay. So some books teach what's called the parallelogram method. So if I take vector V and I add vector U, okay, then I could also have, so this is V, this is U. Technically, this would be V and U. The resultant, which is a new vocabulary word, is going to be the diagonal of the parallelogram. So the black line is our resultant, and the resultant is going to be the net effect. So when I add multiple vectors, multiple forces together, what happens when I add them? And that's going to be my resultant. I typically do not draw the entire parallelogram. So I would draw vector V, I would draw vector U. So this is V, this is U. Notice my U's have tails in case you're wondering. So my resultant would be here, okay? And then that resultant is going to have an X and a Y for its component form, okay? So if we go back to this situation up here, if I added all of my vectors together from the boat, the wind, and the current, each of those is going to have an X and a Y component. I add down, and there is the X component for the resultant, and I add down, and there's going to be the Y component of the resultant, okay? And there's a little bit of math involved, but we'll get to that in the next section. Alrighty, I can also do my vector addition algebraically, and algebra is often easier. So if my U has components of x1 and y1, and V has components x2, y2, then U plus V is going to equal the x's play together and the y's play together. Okay, and then that would be the component form of adding those two vectors together. On the other hand, if I have a scalar and I want to do that math, and we know that it changes the size of the vector. So to change the size of a vector, that means that we're going to multiply. So my new vector, the one that is affected by the scalar, would be a growth or decay factor, k, multiplied by x and y. And so because I have a k, I'm going to distribute that on the inside, so the new vector is going to equal k times x, k times y, and of course we put that in pointy brackets. Pointy brackets are something that you do have to be very careful with, and that would be an element for you to lose points on if you are sloppy with your math, and put curved brackets on your tests. We need to be very deliberate with our math. Example number 2, let me get my computer so it's happy. Example number 2, we're going to be given that V is a negative 2, 5, and we're going to be given W is 3, 4, and I want to find 2 times V, W minus V, and V plus 2W. Okay, so I'm going to set each problem up separately. If I do 2 times V, I'm just going to write this here so you know what kind of math we're doing. That's a scalar. Okay, so it's going to be 2 times the component form of V, negative 2, 5, and this is just going to be a negative 4, 10. So then that's going to equal 2V. That was pretty easy. If I do W minus V, I'm just going to do that simple math. So I'm going to take the vector W, which is 3, 4, and I'm going to subtract vector V, which is a negative 2, 5. The negative applies to everything on the inside of the brackets. So this is going to be 3 plus 2, and then I'm going to have 4 minus 5, and then W minus V is going to equal 5 and a negative 1. So not very complicated math. All right, if I do V plus 2W, I'm adding and I'm multiplying by a scalar. So it's going to be my V, negative 2, 5, added to 2 times W, which is 3, 4. So this is going to be a negative 2, 5, added to 6 and 8. Okay, and I'm out of room, so let me go over here to the next page. So V plus 2W is going to equal 4 and 13. Okay, so the math is pretty easy. As we move to the next section, we'll talk about the math that we're going to show for adding our vectors. But if I'm doing a problem like my boat problem that I threw on the floor, okay, bring back my boat. If I'm going to do a situation where I'm looking for the net effect of multiple forces, I'm going to add each component, each vector in its component form, and then I'm going to get my resultant. And we'll talk more about that in the next video. Alrighty, that is it for today. I will see you soon.